Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE Preparation app from Google Play Store. The link is available in the description of video. So while we were discussing Bernoulli's equation, if you recall, before that we covered one of the very important equations, which is Euler's equation, Euler's equation also we can call it. So in that expression, while deriving, if you recall, this was the free body diagram that I had drawn in the derivation of Euler's equation. This is a streamline, this line is a streamline, and on that streamline I considered a small mass, right? I took it as m, or you can say it to be dm, small mass. And then we looked at all the forces acting on that mass, excluding viscous forces, right? Where we considered the pressure force, the gravity force. Viscous forces we did not consider in the Euler's equation. When we are going to consider the viscous effects, what is going to happen, that is something that we cover later on. When we consider the viscosity of the fluid and we write the equation for viscous flow, then we got the Navier-Stokes equation. That's a separate equation that we get. But if you ignore the viscous effects, then the equation that you get by balancing the force, or you can say by applying Newton's second law along a streamline to a mass, then the equation that you get is Euler's equation or Euler's equation, right? We have done that derivation already. This is the expression that we get, right? We balance the forces along streamline. That's why small s I have written, right? So this s is representing the streamline. So for this mass, I have written the complete mass, the complete force balance. Net summation of all force is equal to mass of this multiplied by the acceleration of this along the streamline, right? This was the expression that we wrote there. I have already explained this complete expression, right? Difference of pressure forces, one from here, other from here. The cos component, this angle is theta, right? In this angle is theta. So weight is going to have a cos component in that direction. So this is why cos is coming. All of this I have already discussed. Acceleration, total acceleration we have written here. The convective as well as the local one, right? But what we did there, since we considered the flow to be steady, right? So this term del V by del T was 0. So we got this Euler's equation or Euler's equation for a steady flow. And then we integrated it to get the Bernoulli's equation that also was valid for a steady flow, because here itself we put dV by dt or del V by del T as 0. So this Bernoulli's equation, a very important equation that we know, is for steady flow. As I told you, viscous effects we ignored. But there can be viscous losses, head losses, major or minor losses. So we already know that what to do in the Bernoulli equation, how to modify the Bernoulli equation to fit the minor or major head losses, right? We already know that. But what about the situation when the flow is unsteady? How do you modify the Bernoulli's equation for an unsteady flow? That we are going to discuss now. Please note, whether it is fluid mechanics or engineering thermodynamics, even heat transfer, in these three subjects, the discussion of steady and unsteady flow is going to occur mainly. Whether it's the flow of fluid or flow of heat. But these situations arise, even the flow of mass also in thermodynamics, even the flow of mass also we discuss slightly in the unsteady case also. So in these situations, flow of fluid, which is kind of flow of mass, right? In thermodynamics also we deal with gases, some parts we discuss with solid also, but gases and liquids also we deal with in thermodynamics. So a general term would be mass flow, right? So the flow of mass or the flow of energy in the form of steady or unsteady. These are the broad classification, right? Steady flow of mass, we discuss continuity equation, right? Steady flow of energy also we discuss in fluid mechanics. What is Bernoulli's equation, right? Same thing. Thermodynamics, first law, same thing, right? So steady flow for mass and energy we discuss, but when it comes about unsteady flow, then if I talk about the exams that you have to write, you will see very less questions from unsteady, very less discussion from unsteady. That does not mean it cannot be asked, right? Very rarely you will see that 1 in 2 years or 3 years you will find some slight concept of unsteady being used somewhere, right? Somewhere means including fluid mechanics, thermodynamics and heat transfer, right? But it is something that you should be knowing. We discuss about unsteady situations in thermodynamics and heat transfer already. But in case of fluid mechanics also, at some places we discuss them. In fluid kinematics, obviously we discuss the mathematical aspect of that. But if we talk about Bernoulli's equation, definitely it has a good use, a good role. It is not going to be extremely important for GATE, because honestly speaking, unsteady cases can be variety of such cases. It depends a lot upon the type of flow, upon the type of container in which flow is occurring, right? Unsteady flow can be of different types. When the flow is getting established, when you just opened the tap, suppose in a pipe, so water is now flowing, it has not even reached to the other end, it is just filling the pipe, flowing. That is the setup stage. Then it slowly increases after filling the pipe, its speed increases, that is the transient stage. Then it reaches the steady state, then you turn it off, then again the same process is repeated in a reverse way. So steady, the unsteady flow can have different types of situations depending upon what case you are looking at, depending upon the shape of the container of the channel in which flow is occurring. So unsteady flow, complete discussion is beyond the syllabus of mechanical engineering at undergraduate level or for any of the exams that you are writing. That is why unsteady discussion, wherever you will see, in thermodynamics also, in fluid also, it will be on surface, basic discussion, right? Because advanced discussion to such an extent that you feel, okay, I have completed unsteady flow in fluid and thermodynamics, that requires you to do higher studies, right? Above BTech. That is why the unsteady flow is not very important, but please note, it's just energy equation, right? So unsteady flow can be asked from Bernoulli's equation also. Obviously, we discussed them in thermodynamics and heat transfer. Right now, we are going to discuss the unsteady flow, the Bernoulli equation for unsteady flow, where this expression we are not going to put as 0. We are going to consider this expression and then we are going to reach to the final equation and see what we are going to get. Let us start. So this is the equation, right, that we were having in the Euler's equation. So let's not put this as 0. Let's keep it and open the bracket here. So this will become PdA with a minus sign. You have PdA with a plus sign. So it will get cancelled. So you are going to have only this term with a minus sign, right? And these are repeated. Now if you look at this small volume here, its weight is mg. M you can write as the density multiplied by the volume. Volume I have taken this area which is dA and the length. It's like a cylinder, you can say. So dA multiplied by height or length, ds will give you small volume dV, right? So this dA ds is same expression I have written here. In this entire expression, you will see dA ds here also, here also. So let us divide this expression with volume. If I do that, this term will be gone, this term will be gone, and this divided by volume, which is this, right? dA ds is volume. You will get m by dV, which is nothing but density. Density is mass divided by volume, right? That's what you get here, right? So dA ds gone, dA ds gone, and m by dV I have written as density. If you look at cos theta, what I told you, this angle is cos theta. You can check the derivation also. This angle was cos theta, right? So if this angle was cos theta, and let me show you here only, this is the length ds, this is the length ds, it is inclined at an angle of theta, this is the angle theta, then this is giving you the change of height, the change of datum, the change of altitude from this point to that point. These 2 points we are considering. Now, across these 2 points we are considering the pressure forces and all. So across these 2 points, how much is the altitude difference? That you can get by drawing such a triangle. This dz you are getting. So this is dz. And now this will help us where? Here. Cos theta. What will be cos theta? This is the base for theta. This is the hypotenuse. So cos theta is dz by ds. So in place of cos theta, we are adding dz by ds. Again, this is something that we have already done in Euler's equation, right? So here we have reached up to this point. ds you can see here also. Multiply the complete equation by ds. This will be gone, this will be gone, and here you will be having a ds. That's what I have written here. And now let us integrate this expression from any point 1 and 2. On the streamline, any point 1 and 2 you can consider. Let's say this is point 1, this is point 2. Integrate that, right? So integration sign we have put here. This integration, which what it is going to give you from 1 to 2. Please note it is with a minus sign, right? So dp is going to integrate to p, which will become p2 minus p1, and since you have a minus sign here, I have put that. Similarly, here also minus sign is coming. Rho g is a constant, density is a constant. So integration of dz will be z2 minus z1. This is the right side expression. If you look at the left side expression, you have two expressions, right? You have a plus sign here. So rho v del v by del s multiplied by ds, integrate, plus rho del v by del t multiplied by ds, integrate from 1 to 2, right? If you look here, their effect will be nullified, right? ds or del s ds for this small point, and you have rho v del v, integration 1 to 2. So what it will become? Rho will come out to be constant out of the integration. Integration of v dv will be v square by 2. So ultimately this will be rho v square by 2 from 1 to 2. Rho is constant, so it will become rho v2 square by 2 minus rho v1 square by 2. That is what we have written here. As you can see here, this term has become this term. Rho v is 2 square by 2 minus rho v1 square by 2, as I explained. And this term I have written here, this particular one, exactly the same. On the right hand side, same term is repeated. Okay, I am just explaining you the steps of integration. The things written in blue color, they will look very related to you. How? Just rearrange them. All the terms on the right side, bring them on the left. Right side will become 0. On the left side, if you rearrange all the blue terms, blue, right? This is what you are going to get. P2 plus half rho g V2 square plus rho g Z2 minus same for 1. What is this? These terms we were getting in the Bernoulli, right? Sum of mechanical energy at point 2 and point 1, right? But here one more term is present. This term is also present because del v by del t is not 0 now. Earlier it was 0. So this whole term was removed and only you are having this is equal to that. There with the minus sign, you put that there on the right side, you will get this sum is equal to that sum. Same as the Bernoulli equation for steady state. But now you have this term as well with 2. So if you bring this term on the right side, you will be having this expression for point 1 is equal to this expression for point 2 plus this term, which is the addition for unsteady Bernoulli equation, right? So from that you will get this. Earlier for steady state, this was the Bernoulli equation because del v by del t was 0. But for unsteady, that is also present. Please note it carefully. Don't do the mistake that you add this on some other side. It will be added on the side of point number 2 because integration is 1 to 2 in that situation. Got it? And now you just need to integrate this. Seems very simple, but think about it. Think about this integration. How velocity is changing with respect to time, that is going to entirely depend upon the condition of unsteady flow. How velocity is changing with the time. It can be very different depending upon the type of unsteady flow. And then you have to multiply it with ds, which is going to get integrated from 1 to 2. Now ds is telling you the streamline length, right? From 1 to 2. ds is what? Any small length. Look at this diagram. What is ds? ds is basically any small length on the streamline from 1 to 2. Now depending upon the shape of the container in which unsteady flow is occurring, depending upon the shape of the pipe, unsteady flow can have variety of shapes of streamlines And that also, in those streamlines also changing, velocity changing continuously. So different shapes of streamlines and changing continuously, their velocity is changing with time. So it's not going to be a very straightforward integration. Don't think it's a very straightforward integration. It will depend upon the container, depend upon the flow, depend upon the unsteady situations. So there is no one fixed answer for this term. That is why you will have to look at the question. What question has been given to you? What situation has been given to you? Maybe question will give you some expression of v with respect to t, using which you can find out the value of this dv by dt. And it will give you the length of the streamline. So you can integrate it with respect to ds from 1 to 2. It totally depends upon the question, what it is asking you. Maybe it will only ask you this expression. Since it's very rarely asked in GATE, unsteady state Bernoulli equation, so you won't see a lot of questions from this. Chances are very less that it can be asked in your GATE. But still, you should know about it. But for whatever situation it will be asked, it will be a simplified problem. For example, we have seen some cases, some unsteady cases. Filling of a tank, emptying of a tank, right? These are unsteady cases only. But they were simplified for a specific situation, right? Same is true for here also. Generally, this type of setup will be discussed for unsteady flow. It can depend upon the question. There is a tank, a large tank, this area having area A1. And from the bottom a pipe is connected having area A2. A1 is very large as compared to A2. A1 is very large as compared to A2. Length of this pipe is L. It is very long. This length is also very long. This symbol is showing a very long length, right? If it was having some steady flow, suppose question gave you it's a steady flow, means that you already opened the knob. If you open the knob here, flow will start, flow will establish. That is unsteady part, transient part, right? Unsteady flow is also called as transient flow. But once the flow is established, then question if asks you something that will come under steady state, right? You may think, how sir, steady state? This will continuously decrease, height will continuously decrease, it is continuously flowing. So how is it a steady state within this reservoir? Because this area A1 is very large as compared to A2, as I told you, it will be given to you in the question. Then this change of height will be very less. You have to wait for a very long amount of time to notice some change of its height. Consider it's a very big lake, very big reservoir, and a small pipe you have attached. Whatever water is going on, the change of level of water, you won't be able to see. It will be very slow, very slow. You can assume it to be a constant. The change of height with respect to time will be very close to zero, maybe 0.001, 002, 003 meter per second, something like that, very smaller value. So we can approximate that to be a steady flow. In that situation, we may ignore the term of unsteady, consider this to be steady. We already know this is the expression for steady, right? Once you have opened the knob, water is moving out, right? So P1, P2 values, let's say here we have cancelled. Question has given us both of them are having atmospheric pressure, right? At point 1, you have the velocity 0 because it is in the reservoir. I told you its velocity is very less. It is moving down very slowly. So the V1 value is almost 0. At point 2, you have considered datum. Suppose this is the datum that you have chosen. So datum for 2 will also be 0. So this datum for 2 is going to be 0. Velocity at 2 it's going to exist. Datum at 1, this is equal to h. Z1 is equal to h, right? So you are going to have what expression? Half rho V2 square minus rho G Z1 is h. So minus rho G h, right, is equal to 0. So it gives V2 is equal to root over 2gh, right? Again, this is an expression which we already know for steady case, right or not? But what about the same situation if I ask you for unsteady? When you have just opened this valve and water is now moving and establishing the flow. In that transient flow, how you are going to write the Bernoulli's equation for this one, right? So you need to make some approximations again for that situation also. Exact value you cannot get. You have to make some approximations unless question has given you a lot of data. It has directly given you the expression of del V by del T. That's a separate situation, right? But here you have to make some assumptions. Assumptions like, again, the pressure obviously same at 1 and 2. Again, even for the unsteady case, you can say, since A1 is very large as compared to A2, so V1 will be in the downward direction, no? it will be here. So V1 will be very less as compared to V2. So V1 you can ignore. For unsteady also we can do it. So V1, this part here, this one will be 0. Pressure will be again atmospheric, this will be 0. This term also will be gone. Again, you are considering this to be datum. So even if steady or unsteady, this term will be 0, right? So you will be having, this will cancel. You will be having this term rho g h half rho v square, but there will be one more term of unsteady that we have discussed earlier. Let us have a look at that, right? In this term will also be present. This is going to be simplified in the same way. Pressure, both atmospheric will cancel. Z2 will be 0. At point 1, velocity is 0. So you have almost, in these expression, you have almost the same terms present. Half rho v2 square here, minus rho g z1, which is h. So minus rho g h. On the right side, it will become plus rho g h. But you have one more term here. Earlier, rho and rho got cancelled. You got, and you multiplied 2 here. Then you got v2 is root over 2gh. Right? But here you cannot do it because this term is also present here. So in this expression now you need to simplify. As I told you, V1, this one we have taken again as 0. Z2t, Z2 with respect to time, it is not going to, wait. Z2t will be 0, not h. Z1t will be h, Z2 will be 0. I think it should be Z1t. Z1t we have taken to be h. Because Z1 here, with respect to time, as we know, it will change. But it is almost, we are taking to be same as h because change is very slow. Similarly, this one is interesting. Velocity at point 2, will it be constant? No. In the case of steady flow, it was definitely a constant number. But here V2 cannot be constant. It is a transient flow. It's establishing, the flow is establishing. Right? But again, within the pipe, that velocity will remain same. It will increase at the same pace. For all the points it will increase at the same pace because flow is establishing right now. So for entire pipe we can take it to be V2. Right? Variation within the pipe between this point and this point, that will extremely complicate the situation, which we don't have to consider. As I told you, we have to take the simpler approach. We have to find out the approximate value. Exact value we cannot find out from this analysis. We need more data to do the exact analysis. So here, that's what we have done. V2 value we have put, which actually depends upon time, this V2 value, right? We know that practically. Even from here also you can see that V value, what is this? Del V by del T, velocity of change with respect to time. Basically, it has two components from point 1 to 2, but two component del V2, when you are going to open it and simplify, that will be existing. We know del V2 by del T exists. Right? Velocity will change with respect to time. But for the sake of this discussion, we have considered the situation where we can replace it only with V2. Only for this expression we are doing it. So don't think it is a constant number. Even in this entire expression, you can see that somehow if you want to find out V2, you need to integrate this. Only then you can find out V2. You integrate this, you need a factor of change with time, which tells you that yes, V2 depends upon time, with the change in time, right or not? So it's not, what I mean to say, it is not a constant value. You must keep that in your mind. It's not going to change your answer as such right now. Now in this expression, again, this integration you need to perform. Question must give you something to be able to perform this integration. If you look at this, what we have done here, that integration which we needed to do, we have broken down into different components. Now this you have to look for the specific case that we are talking about. For the case that we are talking about from 1 to 2, we have broken that down into 3 different paths. Suppose this is a streamline from point 1 to point 2. So that streamline has been broken into 3 parts, 1 to A to B and B to 2. Why we have done that? Because in 1 to A, velocity we are considering 0. Inside the reservoir, area is very large, velocity is very less. From A to B, what is A to B? What is the significance of A to B? Why have we taken the point B here? AB is telling you entrance within the pipe. So 1 to A is reservoir, A to B is the entrance, and then B to 2 is the pipe. A to B can have change of velocity, but it's very less in length. ds is very small from A to B. They are very close to each other. If the entry was gradual, If the entry was gradual, then A to B entry would have some considerable length. Then it would have been a complex problem. But in such case, entry is sudden. So length ds is very small. So if this complete integration I break from 1 to A to B, B to 2, right? Basics of integration, mathematics, we can do that. This integral, we can break down into 1 to A to B, B to 2. So this expression will become 0 because del V is almost 0 in 1 to A because it is within the reservoir. A to B, ds is very small. So that is also gone. Only one integration you need to perform, which is from B to 2. Again, is it the exact process? No, it is going to give you approximate value, right? That's our best we can do for unsteady. So for that case, I mean, for this specific shape, specific situation, that's why I told you it depends upon the shape. Here, if you make the entry like this, a gradual entry, then you cannot make second term as 0. Getting the point? We are taking a simpler form so that we can simplify the analysis and get the answer at our level from the point of view of GATE or any other exam that you want to write. So this integration will be equal to this integration. That is what we have done and written here. Equal to means almost equal to, right? And now, as you can see here, if you perform this integration by considering a constant del Q by del T, suppose del V by del T has been given to you as a constant value, then this term can come out of the integration sign. And within the integration, you will be having ds from 1 to 2 or from B to 2, right? And from B to 2, this integration is equal to length of the pipe. So this you have got. So if you go back to the earlier expression and replace this with this integration, we have simplified and got this expression, right? So where is this expression? Where is this expression? We reached at this expression now for the unsteady case. By simplifying it, this term was present, right? So this integration we opened and simplified, and now the value that we have got, we are going to put it back. That is what we have done here. That value, this we got by integration here, right? We are going to put it back. So we are going to get this expression which we have written here. And now if you simplify this expression, rho will be gone, rho will be gone, rho will be gone. So we are going to have L del B2 by del T plus V2 square by 2 is equal to GH. Do you need to remember this expression? Not at all. You need to remember the process what I did. This is not necessary that GATE will ask you this case only. It's a specific case of Torricelli flow. It's a specific type of flow. GATE can ask you, maybe it cannot ask you unsteady flow. Or it can ask you the same case, or it can ask you slightly different case, or it cannot even give you the case. It can just give you the values and you need to perform just this integration. From the given values, arithmetic values will be given to you, right? That algebraic values will be given to you, right? And you need to put those values here, perform the integration and solve it just like any mathematical question, just like any mathematical expression. But if you don't know this expression, how will you be able to solve, right? So GATE can give you different situations for this, but rest assured they will be simplified cases, right? If you look at this integration, if you integrate this expression, if you integrate, as you can see, you have del V2 and del T. So that integration if you perform, you will get some expression of V2, as you can see here, right? It's a hyperbolic variation, 10 hyperbolic, right? So it basically gives you an idea how velocity is going to vary. We know that the curve of hyperbolic varies like this, 10h curve. This is x, this is 10hx, right? So in this part we are going to see this is how it varies, right? This is how the velocity in general, you can say, varies with time, not exact. This is going to be a different term, t divided by tau. As I told you, this detailed discussion how we reach from here to here, I am not going to go into that right now. L by root 2 GH is called as tau, it becomes T by tau. That is not relevant for GATE. But the point is that this discussion gives you an idea, an approximate idea that okay, in such situation, how velocity will vary with the time. So this is how it is going to vary till it becomes a constant number and the steady flow comes. Got it? So as I was telling you, this exact expression is of no use to you. You don't need to remember this, but you need to know the process which I followed. For example, this case, if you look at This case, this can be a case which can be given to you. Note, there is no length of the pipe given to you, right? Only you have been given up to this point. And now you need to perform this integration, Maybe question will ask you dv by dt only. It will give you all the other values, it will ask you dv by dt only. Considering that to be constant, dv by dt will come out of the integration, rho will come out. You need to integrate ds from 1 to 2. What is ds? Length of the streamline. So this length of the streamline you need to calculate. How? Question will give you something. Question will give you some expression of ds or something using which you can integrate and get the answer. What I mean to say, question can be varied. All you need to do is remember this expression and remember the process of how I simplified this integration. That will help you in whatever question comes.